Good morning, everyone. Welcome to Gate Electronic Devices. And today's topic is we are learning about diodes. Actually, in previous classes, we have learned about semiconductor physics. Under that, we have learned about different topics and where semiconductor physics is carried by 4 marks. Now, let us start the concept of diodes here, where the diodes comes for gate examinations, right? So, let us see, this is the syllabus for diodes in gate examinations, where it is contained by PN junction diode, GNR diode, light emitting diode. It's a special diode, and another special diode which is a photodiode, and another one is a solar cell. So these are the topics we will be learning in diodes, and these topics is carried by 3 marks, and it comes under gate examinations. And most probably all competitive exams, all government sector, public sector undertaking companies, they will be asking this topic which is called as diodes, right? Let us see what is this diode and what is the brief explanation of this diode here. Here, before going to diode, we need to learn about what is vacuum tube actually. It's a vacuum diode. What is vacuum diode? Actually, before invention of a diode, vacuum diode is present. But we are not using this vacuum diode. Previously, we have been using this vacuum diode. Why we are not using this vacuum diode means this vacuum diode is having some disadvantages. What are those disadvantages means? The disadvantages of vacuum diode are like this. This vacuum diode is bulky in nature. It is bulky in nature, and also this vacuum diode is costly. It is too costly to buy that vacuum diode, and it is also noisy. It produces more noise, buzzing sounds while the signal is being transmitted, right? If it picks the signal, it gives more sound as that of the present radio systems. And also it takes more time for conduction. It takes more time for conduction. That means its a cut-in potential is very, very large because it is taking more time for conduction. So because of these disadvantages of vacuum diode, the scientists have been shifted to ordinary diode, which is called as a PN diode. So let us see what is this PN junction diode or PN diode and how it is formed, how it is constructed actually. So PN diode, the name itself tells you it is a combination of P-type and N-type semiconductors. It is a combination of P-type and N-type semiconductors. So you can see here, this is a P-type and N-type. So what is P-type and how it is formed? A P-type semiconductor is formed by taking a pure silicon crystal or germanium crystal, and it is doped with the P-type impurities. So take a pure silicon or germanium crystal, and dope this one with the P-type impurities. You know already what are P-type impurities. Actually, we have discussed in semiconductor physics what are P-type impurities. The P-type impurities are, for example, boron, aluminum, gallium, and indium. Right. These are the P-type impurities, where the outermost orbit contains only 3 electrons in that outermost orbit. So therefore, these are all called as acceptor impurities. They will accept the electrons. So all third group elements are P-type impurities. So if you add any one of this boron or aluminum, gallium or indium to this pure silicon crystal, it will form a P-type semiconductor, right? Similarly, the N-type semiconductor to a pure silicon or germanium crystal add N-type impurities. What are N-type impurities? The majority charge carriers are electrons. All pentavalent impurities are N-type impurities. What are they actually? We have learned already N-type impurities like phosphorus. We have learned about phosphorus, arsenic, antimony, arsenic, antimony and bismuth, where these elements are having at outermost orbit 5 electrons revolving around the nucleus. So they are all called as a donor elements. They will donate an electron to other atom. So therefore, if you add this type of elements to silicon or germanium, it will form n-type semiconductor. As you see here, the structure of a diode, the p-type semiconductor is been merged with the n-type semiconductor. It's been combined and there forms in between p-type and n-type at the center point, which is called as a junction. This is called as a junction J. This line is called as a junction J, where it is acting like a boundary between p-type to n-type semiconductor. Now you can see here p-type semiconductor, the majority charge carriers are holes, and there are also some minority carriers which are called as electrons. Here this is an n-type semiconductor where majority charge carriers are electrons and some minority charge are also present which are nothing but holes. So here majority charge carriers are holes. Holes are of all positive charge particles, because hole, as you know that whole majority charge carriers are holes. Holes are all positively charged particles, and minority also present here which are nothing but electrons. Electrons are of negatively charged particle. Now here n-type semiconductor, similarly here majority charge carriers are electrons. Majority charge carrier electrons and they are of negatively charged particle, and minority charge will be present. Those are nothing but holes, and the holes are of positively charged particle. Okay. So this is the structure of PN diode, where you have all holes and all electrons present here with respect to positive charge and negative charge. Now here you can treat every hole, a positively charged particle, as an atom, as an atom or a molecule, as an atom or a molecule. So this atom will donate an electron or it can accept an electron. If it donates an electron, it will form as a donor impurity. If it accepts an electron, it is nothing but an acceptor impurity. So therefore, this atom can donate an electron or accept an electron. All holes, definitely they will accept electrons, and all electrons, they will donate one electrons, right? So these are called as ions. An ion is an atom which donates or accepts an electrons. So here let us see the same structure in the form of ions. For example, here n-type, here electron, it will donate one electron and it will form an ion which is called as a donor ion. So everything here, all electrons will donate one electron and will forms an ion. Electron forms an ion. Likewise, this is called as a donor ion. I can treat this one as donor ion, and this dot is called as an electron. This dot is called as an electron. This dot is an electron, and this dot is negatively charged particle. This dot is negatively charged particle. Right? Similarly here, a positively charged particle atom is there. This atom, a positively charged particle, it accepts an electron. So therefore, this plus will have a hole behind it and it will form an ion. That ion is called acceptor ion. So like minus round, this is called as an acceptor ion. Nearby it a hole will be present. This is called as an acceptor ion. And this is called as a hole. Likewise, hole complete this structure. There are acceptor ions combined. Nearby it a hole will be present. Acceptor ion and a hole. Acceptor ion and a hole will be present. Here completely a positive donor ion and an electron. Donor ion and electron. Donor ion and electron. Right? So we are representing PN diode in terms of ions actually. Right? Let us see the complete structure here. How the PN diode is represented in terms of ions. So this is a complete structure which is contained by p-type and n-type. Center is the junction. Now here this is called as an acceptor ion, where it accepts an electron, so therefore it will have a hole nearby it, and this hole is a positively charged particle. And remember, these holes are responsible for flow of current, not ions, because atom, it is donating a hole and accepting an electron. So after donating and accepting an electron, then no way it is responsible for current flow. That hole which is nearby it or electron nearby it, that particle is responsible for flow of current. Now here the holes which are positively charged particle are responsible for flow of currents. Here similarly here a donor ion is there here, plus around, this is a donor ion, where ion it is no way depending on flow of currents, but the electron beside sits, which is a negatively charged particle. This electron is responsible for flow of current. Okay, so remember this point, this electron is responsible for flow of current. Now here, after forming this structure like this, with respect to donor ions, electrons, acceptor ions and holes, let us see how does current flows in this diode, or what are the internal calculations that are being placed and happened in this diode. This type of diode, I am not applying any external energy or external voltage, so that this type of junction, PN junction combination is called as open circuit PN junction, because I am not applying any external electric field or external potential, so therefore it is called a open circuit PN junction. So this open circuit PN junction, let us see what happens for this open circuit PN junction and how does current flows in this device after applying external potential, right? So let us go deep into this PN structure with the combination of ions, which is a donor and acceptor ion, electron and hole. Now see here, this is a junction here, where this junction, it is carried by hole, here it's carried by electron, and these are only the responsible one for the flow of current. Now here, since they are very nearer to each other, this is a junction, this electron and this electron and this a hole very near to the junction, they will cross the junction. They will cross the junction and they will get recombined, because this electron comes and fill into this hole, therefore it will get recombined and this will exhaust. This electron gets recombined, this will exhaust. Nearby charge carriers recombine, exhaust. Nearby charge carriers recombine, exhaust, leaving there only immobile charge carriers. This is immobile charge carrier, which is called as negative charge. This is called immobile negative charge. Immobile negative charge. That is called immobile negative charge. Similarly, that side, this holes, this electrons are been vanished away, leaving there only immobile charge. That immobile charge is a positive charge. So this is called immobile positive charge. This charge will not be moving from one point to another point, because it's nothing but an ion. Ions will not move from one point to another point. Only besides it, electrons and holes, they will be moving, they will be creating current flows, right? So this is immobile positive charge. That is immobile positive charge. So the region where immobile charge is present, that region is called depletion region. Remember, this region is called the region where immobile charge, positive charge and negative charge is present. That region is called depletion region, or it is also called by another name as space charge region. Space charge region, or it is also called as transition region. It is also called transition region. So it can be called by three names: depletion region, transition region, or space charge region. At this region where immobile charge is present, that region is called depletion region or space charge region or transition region. So approximately, if you take a PN diode, this depletion region is approximately, it is of width is equal to, for ideal diode, its width is equal to 1 micrometer. Remember, its width is 1 micrometer, means that is equal to 10 power minus 6 meters. 10 power minus 6 meters. This is the ideal value of depletion region for ideal diodes, where the width of depletion region is 10 power minus 6 meters. Similarly, the width of complete diode structure, combination of P and N, this complete P and N structure, the ideal value is, it is equal to 0.5 centimeters. Remember, these are the ideal values of a PN diode where the complete structure is 0.5 centimeters and the depletion region width is only 1 micron, that is equal to 10 power minus 6 meters. 10 power minus 6 meters. Okay, right. Now let us see some important concepts which are present in this open circuit PN junction. Okay, let us learn about the important concepts here in a PN junction. Okay, so I told you this is a p type and n type. These are acceptor ion and a hole, and this is a donor ion and an electron, and in the center a depletion region where immobile charge is present. This is a negative immobile charge, this is a positive immobile charge, and here various concepts comes into existence. Let us learn all those concepts. This is the junction where I am drawing here, and this is a depletion region. Please remember, in open circuit PN junction there are various concepts that comes into existence. Let us learn all these concepts which are very important for competitive exams. Very important for competitive exams. So this is a depletion region. Assume this is a width of negative charge, and this is assume this is a p type. So therefore I assume this one is width of negative charge as Wp, and this is a width of positive charge, where width of positive charge in n type, that is Wn. And here acceptor concentration will be present. I can write this one as acceptor concentration as Na, which are nothing but holes. These are donor concentrations. I can write this one as Nd, donor concentrations as Nd. Now, there is a important formula for competitive exams. The charge here acceptor concentration Na and width of this depletion region for p side is Wp, this is Wn, and this is Nd. Now I can write this one as at the equilibrium position or at a constant temperature, what happens is the charge density in p-type semiconductor, into volume of p-type semiconductor is equal to charge density of n-type semiconductor into volume of n-type semiconductor. Okay, so now what is this charge density? We have already learned charge density is nothing but it can be written as P into E or N into E. So therefore I can write this one as for p-type semiconductor as acceptor concentration Na into mobile charge carrier as E, electron charge as taken as E. Similarly volume is taken as length into area. What is the length of volume of P? Length of volume of P is Wp, and area is I am taking as area. It is nothing but volume. Volume is equal to Wp into area. Similarly here charge density in n-type, I can write this one as Nd into E charge into volume is the length of depletion region in n-type and area. So both are at equilibrium position because it is at a open circuit junction. So therefore I can write this one as rho p into volume of p-type is equal to rho n into volume of n-type. Rho is called charge density. So therefore charge density is given by Na into E gets cancelled, area gets cancelled. So therefore I have here Na Wp is equal to Nd Wn. Okay, or I can write this one as Wp divided by Wn, width of depletion region towards p side and width of depletion region towards n side. Wp divided by Wn is equal to Na divided by Nd. Na divided by Nd. For example, case 1, if the semiconductor is a p-type semiconductor. If it is p-type, then Na is double greater than Nd. If it is heavily doped, p-type is heavily doped than n-type. So therefore acceptor concentration is larger than donor concentration. So at that time what happens? If Na is greater than Nd, then width of depletion region is more towards which side? That is the important point here. So if acceptor concentration is greater than donor concentration, then therefore width of depletion region Wp Na, that means Na means what here? Acceptor concentration Na is larger than that of donor concentration. So therefore, so width is large towards which side actually? So width is large towards Wp is greater than Wn. Width of p side is greater than width towards n side. Wp divided by Wn is equal to Nd divided by Na. Nd divided by Na. Nd divided by Na. So therefore, if it is a p-type semiconductor, then Na is double greater than Nd. Then what happens here? Na is double greater than Nd. So therefore, Na is double greater than Nd. So therefore, Wp is Na is greater than Nd. So acceptor concentration is larger than that of donor concentration. Then width of depletion region is more towards n side. Width of depletion region is more towards n side compared to that of p side. Okay, width of depletion region is more towards n side. Similarly, if it is n-type semiconductor, Nd is greater than Na. Donor concentration is larger than acceptor concentration. Then what happens is width of p side depletion region is greater than width of n side. Wp is greater than Wn. Okay, this is for n-type semiconductor. Because the concept is here is, if it is heavily doped, then there is a possibility that more charge carriers diffuse and then recombine here in n-type semiconductors. So therefore Wn is greater than that of this one. Similarly, this is heavily doped n-type, then there is a possibility that more electrons diffuse into p-type. So therefore depletion region widens here. So therefore Wp is greater than Wn. This is the concept and this is the important formula you need to consider here, right? Next, coming to this point of important points here. The first point is called charge density. Charge density. What is the charge density present here? So charge density is given by the formula d square v by dx square is equal to minus rho by epsilon. This is the formula for charge density. D square v by dx square is equal to minus rho by epsilon. So if you consider here, if I draw a graph here, what is the graph here? This is called distance x. I am taking this one as distance x, and this is x is equal to 0. This one distance x increases here. So what happens? Charge density here, all positive charge is present. So therefore, if you combine all this positive charge in the depletion region, you have a plenty of positive charge. So therefore, this positive charge is given as like this. This is a positive charge, and this is all completely negative charge. So therefore, if you combine all that negative charge, so therefore you get a negative charge here like this, complete negative charge. So this is called as charge density in the depletion region, right? This is the first point of to be studied. Second point, electric field intensity. What is electric field intensity? Electric field intensity is given by E, and E, already we know electric field intensity E is equal to dV by dx. So dV by dx means, what is the formula here? I want to get dV by dx, so I need to integrate this one. If I integrate that one, then I get minus rho by epsilon into dx. Okay, so this is the electric field intensity. But what is the electric field intensity if you draw a graph as distance you take, distance from the junction, this is x is equal to 0 and this is x is increasing. So what is the electric field intensity? The electric field intensity is, as you know, always remember the electric field intensity starts from positive concentration to negative concentration in anti-clockwise direction. In clockwise direction. See, this is it is starting from positive side and it is going to a maximum value here at x equal to 0 and reducing here in a clockwise direction. So therefore, this is completely called as electric field intensity. So remember, electric flux lines starts from positive and ends at a negative side in clockwise direction. So therefore, this is electric field intensity which is given here. Third point, and remember at x equal to 0, the electric field intensity is maximum. Electric field intensity is maximum. This is a maximum value of electric field intensity. At x equal to 0, you get maximum value of electric field intensity. Third case, potential energy barrier for holes. What is the potential energy barrier for holes? So here actually this hole is not moving towards that side and this electron is not moving towards this side, because this hole tries to move towards this side but it is overcome by positive charge here and repels back and then comes over here. And similarly this electron comes here near the junction, but it will not cross the junction because it is not having that much of energy to cross the junction. So therefore it is overcome by this negative charge. It will repel back and again sits in original position. So that's why all the second column electrons, third, fourth column electrons are not crossing the junction because they are not having the required energy to cross it. Similarly here also all second column holes, third column holes, fourth column holes, they are not crossing the junction because they are not having required energy. They will come to junction, near the junction, and due to this positive charge they will be repelled because it is a positive charge and therefore moves backwards and sits in the original position here. All these holes are moving with respect to diffusion. Remember, all these holes are moving with respect to diffusion. As we have studied already in semiconductor physics, without applying any external electric field, the concept is nothing but diffusion. And the current produces diffusion current, right? So this is due to diffusion because I am not applying any electric field. So therefore, this charge carrier moves from this point to this point and diffusion exists. If diffusion exists, diffusion current density also exists. And this is due to holes, so therefore diffusion current density due to holes exists. Similarly, electrons also moves towards this side, so therefore due to diffusion this will exist. Due to diffusion this will exist. But after reaching here in the junction, what is existing in the junction? Is it diffusion or drift? Definitely it is drift, because this is a charge carrier. It is been repelled by this negative charge due to this charge. So applied potential is being affected. So therefore in the junction drift exists. In the junction, inside the junction drift exists. Inside the junction drift exists because inside the junction all charge carriers are being affected by this positive charge and also electrons are being affected by negative charge. So remember, outside the junction diffusion exists, inside the junction drift exists. Okay. Now the potential energy barrier for holes. These are all holes. Holes are not moving from the p type to n type because they are overcome by this positive charge here, positive barrier which is present in inside the depletion region. So therefore if you draw a graph for that one, then you have with respect to distance x, the positive energy barrier is how much? This is all positive, so therefore positive is x equal to 0 above the x-axis, so therefore you get a positive energy barrier like this. This is completely called as potential energy barrier for holes. Potential energy barrier for holes, and this is given by V0, which is the potential energy barrier for holes. That means holes has to acquire this V0 potential to move from p type to n type. If they do not acquire this V0 potential, they will not cross and create current existing from p type to n type. So that's why this is called the potential energy barrier for holes. This is V naught is equal to 0. Potential is equal to 0. Fourth point, last point, important point here, potential energy barrier for electrons. Potential energy barrier for electrons. What is the potential energy barrier for electrons? All electrons from this side, they are coming to junction, but they are not crossing the junction. Why? Because they are overcome by a negative charge near the junction in depletion region. So therefore, if they want to, all the electrons want to cross this junction, they need to acquire more energy than that of this potential energy barrier. So that's why they will not cross the junction, right? So if you draw a graph for this, the graph will be like this, distance x, all this negative charge is below the x-axis, so, or you can write in the positive charge also, right? So this is the potential energy barrier for electrons, provided that this is equal to E naught, and this E naught equal to 0 is lying at this point. E naught is equal to 0. And below this one is a negative x-axis because it is of a negative sign. So therefore, it is negative. Or else you can draw another graph here like this. The same similar graph can be drawn in downwards like this. If this is the depletion region, since negative charge is below x-axis, so you can draw here like this. This is called potential energy barrier for electrons. So this gap is nothing but it is called E naught. Now this is called E naught is equal to 0. Previously this is E naught is equal to 0. This point is called E naught is equal to 0, where below this point it is negative because this is a negative charge. And now here we can draw this graph also. E naught is equal to 0. Below this graph it is a negative value because all electrons are present here. This is nothing but negative charge present here. So this is a graph for potential energy barrier for electrons. This can be written also, drawn also like this, right? So these are the important concepts in open circuit PN junction what we are studying, right? Let us solve some problems here which comes under competitive exams. First one, which of the following is true? A silicon wafer heavily doped with boron is a P plus substrate. A silicon wafer lightly doped with boron is a P plus substrate. A silicon wafer heavily doped with arsenic is a P plus substrate. A silicon wafer lightly doped with arsenic is a P plus substrate. So if the question is like this, how to answer this type of question here? Suppose boron. What is boron? Boron is a p-type impurity or n-type impurity? Definitely it is a p-type impurity. Definitely it is a p-type impurity. What are p-type impurities? Boron, aluminum, gallium and indium. Boron, aluminum, gallium and indium, baggy. So this is a p-type impurities. Boron is a p-type impurity. So therefore, now it has been asked a P plus substrate here. What is P plus substrate? Actually, we have learned about only P, no? P-type and N-type semiconductor. But what is P plus substrate? P plus substrate is a heavily doped semiconductor. We have three types of semiconductors here. Like we have P minus, P and P plus. What is P plus? P plus means for every 10 power 3 parts, for every 10 power 3 parts, one part of impurity is added. One part of impurity, for every 10 power 3 parts, one part of impurity is added. This is a heavily doped semiconductor. This is called heavily doped semiconductor. Heavily doped, right? That is why it's called as a P plus. What is P? It is moderately doped semiconductor. I can write this one as 10 power 6 parts. For every 10 power 6 parts, one part of impurity is added. One part of impurity is added. So therefore, I can write this one as moderately doped. Moderately doped. And P minus is for every 10 power 8 parts, one part of impurity is added. One part of impurity is added. So this is called lightly doped semiconductors. This is called lightly doped semiconductors. So remember, P minus means 10 power 8 parts lightly doped, P means 10 power 6 parts moderately doped, P plus means 10 power 3 parts heavily doped semiconductors. Now using this one, silicon wafer is heavily doped with boron is a P plus substrate. Okay, a silicon wafer lightly doped with boron is a P plus substrate. Lightly doped means P plus will not come under lightly doped. This is wrong. Silicon wafer heavily doped with arsenic. Arsenic means it's an n-type impurity. What are n-type impurities? N-type impurities: PAB, phosphorus, arsenic, antimony, bismuth. But arsenic, it must be a N plus. So therefore this is wrong. Silicon wafer lightly doped with arsenic. Arsenic is n-type. This is wrong. So answer is A. A silicon wafer heavily doped with boron is a P plus substrate. Heavily doped with boron is a P plus substrate. Okay. Next one. The switching speed of P plus N junction depends primarily on. What is the switching speed? That means charge carriers that has to move from P to N type or N to P type. So it depends on what actually? Actually the switching speed depends only on the lifetime of charge carriers, not on mobility of the charge carriers. So therefore here wherever mobility is present, it is wrong. So mobility of minority carriers in the P plus region is wrong. The lifetime of minority carriers in the P plus region. Mobility here also C is present. Mobility of majority carriers in the N region. The lifetime of majority carriers in the N region. It depends on only minority charge carriers. Lifetime of minority charge carriers is depending on the switching speed of the device. So therefore the switching speed of P plus N junction depends primarily on the lifetime of minority carriers in the P plus region. Please remember, lifetime of minority carriers in the P plus region. Next, in a uniformly doped abrupt PN junction, the doping level of the N side is 4 times given. What is given? Abrupt PN junction is given. Doping level N side means donor concentration is equal to 4 times than that of doping level of P side. P side means doping level is acceptor concentration. It is equal to 4 times of Na. Then the ratio of depletion layer width is, I already told you the concept, the depletion layer widths. What is the formula? Acceptor concentration into width of depletion region towards P side is equal to donor concentration into width of towards N side. So therefore Wp divided by Wn is equal to Nd divided by Na. So he has been asked the ratio of depletion layer widths, means this is depletion layer widths. So Nd is equal to 4 Na. So Wp by Wn is equal to 4 Na divided by Na. So Wp is equal to the ratio, then the ratio of depletion layer widths is Wp by Wn is equal to how much? 4. So the answer is 4. So thank you so much. We'll stop over here and we'll continue in next class.